Section 5.4, Fundamental Theorem of Calculus, Part 1. So the fundamental theorem, otherwise known as the integral evaluation theorem, states that if f is continuous at every point on the interval a to b, and if capital F is any antiderivative of f on the interval a to b, then the integral from a to b of f of x dx is equal to capital F of b minus capital F of a. So remember, the capital F's are the antiderivatives. So the way that we find this, there are 3 steps. So the first step is to first find the antiderivative. Okay, so our first step is to first find the antiderivative. Our second step is to substitute the limits. And then our last step is to subtract. So we have 3 examples that we're going to work through. First, we want to evaluate the following definite integrals using the fundamental theorem of calculus, then check our answers using numerical integration on your calculator. So first thing we want to do for number 1, we have the integral from -1 to 2 of 6x squared minus x dx. So first thing we want to do is find the antiderivative of 6x squared minus x. Okay, so the antiderivative of this, right, we're going to add 1 to the exponent, so we have x cubed, divide 6 by 3, we get 2, minus, add 1 to the exponent, we get x squared, divide 1 by 2, we get 1/2. Okay, so that's our antiderivative for this function. All right, and there's one thing that we're going to add to this. So when we're doing this, just a quick clarification, when we're doing this, we do not need to add the c because we're actually going to find the antiderivative from -1 to 2. So instead of adding c, since we're going to be on this is a definite integral, right, it gives us a starting point and an ending point, we're actually going to put that starting point and ending point here, because this is going to tell us this is the antiderivative. We don't need the constant because we're going to look for the antiderivative from -1 to 2. So this is now where we put our limits. Alright, so now what we're going to do is we are going to substitute our limits. So b is our upper limit, which is 2, so we're going to substitute 2 into our antiderivative. And a is our lower limit, so we'll substitute -1. So we substituted our limits, and now we just evaluate and subtract. So here we have 16 minus 2. And we're going to subtract 2 plus 1/2. 16 minus 2 is 14. 2 plus 1/2 is 2.5. So we add those. Oops, sorry, this is -2. So we subtract these and we get sorry about that, minor sign error. This should be negative. -1 squared is 1, so this should still be negative. So now when we subtract everything, we get 16.5 So that is the solution for the integral from -1 to 2 of 6x squared minus x dx. So now let's look at the integral from -pi/2 to pi of cosine x dx. So again, our first step is still to find the antiderivative. So the antiderivative of cosine x is sine x. And again, we don't need the plus c because we have limits here. We have a lower limit and an upper limit that we're looking at, so we're just going to rewrite those over here. And now we're going to substitute those limits in. So we have our upper limit, which is sine pi, minus our lower limit, so sine of -pi/2. And now to evaluate and subtract. So sine of pi we know is 0, and we're going to subtract sine of -pi/2, which is -1. So 0 minus -1 is 1. And then our last integral from 1 to 4 of 6 over root x dx. So what I actually want to do for this is I want to rewrite this in a way that we can see how we would find the antiderivative. So I'm going to rewrite this whole integral. We're going to go 1 to 4 of 6 times, and then square root of x, when it's at the bottom of the denominator, is just x to the -1/2 dx. Right? The negative exponent transfers to the bottom of my fraction, and the 1/2 is where we get the square root sign. So now that we have that, I'm going to find the antiderivative of this. So the antiderivative of this, we would have to take our exponent and add 1, so that brings us to 1/2. And then we divide our coefficient by our exponent. So 6 divided by 1/2 is 12. And again, since we have limits, we're going to go from 1 to 4. And we can rewrite this as 12 root x from 1 to 4. So now, substitute and evaluate. So our upper limit is 4, so we have 12 square root of 4 minus, and then our lower limit is 1, so 12 square root of 1, which gives us 12 times 2, which is 24, minus 12, so our answer is 12. Now to check our answers, we could plug into our calculator so that we can check to make sure that we get 16.5 for our first integral, we get 1 for our second, and 12 for our third. So now let's move on to page 2. Finding total areas. So to find the area between the graph of y and the x-axis over the interval a to b, there are 3 steps. So the first step is to figure out what are the zeros of the function on the interval a to b, if they exist. Second is to then integrate the function over each subinterval, which is what we did on the first page. And then the last piece is to add the absolute values of those integrals. So just a reminder, we're looking for the total area. We're not looking for the area above the curve minus the area below the curve. We're looking for the total area, so therefore we need to add the absolute values of those integrals. So for our first example, we want to find the total area of the region between the curve y equals 4 minus x squared, and the x-axis from 0 to 4. So our first step is to find the zeros of the function on the interval 0 to 4. So to find that, we have 4 minus x squared, and we're going to set that equal to 0. Okay, so one thing we can do here is we can factor. So we have 2 plus x, 2 minus x equals 0. And when we set 2 plus x equal to 0, x is equal to negative 2. And when we set 2 minus x equal to 0, x is equal to 2. So on our interval from 0 to 4, the only one of these zeros that exists is x equals 2. So we can reject that 0. So this is the one that we care about, because it's on the interval that we're looking at. Now the second step is to set up and evaluate the definite integral for each region of the graph. So now, if we think about it, we're going from 0 to 4, and we have a 0 at 2. So what we're going to do is we're going to integrate from 0 to 2, and we're also going to integrate from 2 to 4. Okay, so our first integral will be from 0 to 2 of 4 minus x squared dx. Okay, so to integrate this, right, the antiderivative of 4 is going to be 4x. The antiderivative of negative x squared, we're going to add 1 to the exponent, divide the coefficient by our new exponent, so we get 1 over 3. And we're integrating from 0 to 2. So now we're going to substitute and subtract. So we have 4 times our upper limit, which is 2, minus 1/3, 2 cubed. And we're going to subtract from that 4 times our lower limit, which is 0, minus 1/3, 0 cubed. And when we do that, we get 16 over 3. I might just run out of space, but I'll try my best here. Okay, so that's from 0 to 2. So from 0 to 2, we got 16 over 3 as our area. Now from 2 to 4, we're going to integrate the same equation. So we still have the same antiderivative, but now we're going from 2 to 4. So when we substitute, we have 4 times 4 minus 1/3, 4 cubed, minus 4 times 2 minus 1/3, 2 cubed. And when we do that, we get negative 32 over 3. So we have negative 32 over 3 as the area from 2 to 4. So now our total area will be the absolute value of 16 over 3 plus the absolute value of negative 32 over 3, which will give us 48 over 3, which reduces to 16. So the total area of that integral from 0 to 4 is 16. Okay, and if you want to check that in your calculator, to find the total area, we have to make sure that we're putting that equation in absolute value, because we're looking for not the area above minus the area below, but the total area as a positive number. Okay. Now, for the last page of part 1, we're going to talk about the average or the mean value of a function. Okay, so we're going to let y, av, be the average value of a function of f on the interval a to b. When f of x is greater or equal to 0, the area of this rectangle here is equal to the area under the graph of f from a to b. Okay, so what this is saying is that if this is the average, if this is what you get for a y value when you find the average between a and b, then this area for the whole rectangle should be equal to the full area under the curve. So if I were to move this over here, that should complete my rectangle. Okay? So the area of the rectangle, base times height, is equal to the area under f of x. Okay, so b minus a, right, my base times my height, because my height is now the average y value, is going to be equal to the integral from a to b of f of x dx. So now to find the average y value, I would then divide this by b over a, right? So my average y value is equal to 1 over b minus a times the integral from a to b of f of x dx. Okay? So to find my average value of the function of f of x on any interval from a to b, I would take 1 over my higher limit minus my lower limit and multiply all of that times the integral from my lower limit to my higher limit of the function in terms of x. So for number 1, we want to find the average value of f of x equaling the square root of x on the interval from 1 to 9. So I know that I'm going to need to find the integral of the square root of x. So I'm just going to rewrite this as x to the 1/2 from the beginning. Okay, so when I plug this in, I know that I'm going to have 1 over my higher limit minus my lower limit, so 9 minus 1 of the integral from 1 to 9 of x to the 1/2 dx. Okay, so then 1 over 9 minus 1 is 1 over 8. And we're going to multiply that by, and if we find the antiderivative of x to the 1/2, right, we're going to add 1 to our exponent, so we have 3/2. And then we're going to divide our coefficient by our exponent, so we'll get 2 over 3. Okay, and we want that from 1 to 9. Okay, so now we still have our 1 over 8, and we're still going to multiply that by 2/3 9 to the 3/2 minus 2/3 1 to 3/2, which is going to be equal to 1/8 times, oops, I might run out of some space, 18 minus 2/3, which is equal to 52/24, if you can simplify to 13/6, or if you want to plug it into the calculator, approximately 2.167. So that's the average value of f of x on the interval from 1 to 9. Now for question number 2, we have the outside temperatures were recorded every hour from noon until midnight. We want to estimate the average temperature for the 12-hour period using trapezoids. So we have not yet looked into how to find the area under a curve using trapezoids. That's actually 5.5. So what we're going to do is we're going to table this question until 5.5, and then we'll revisit it at that point. Okay, so that's the end of the part 1 of 5.4. If you have any questions, please do not hesitate to bring them up in class tomorrow.